There's a point where relational and document models both start to struggle. It happens when the relationships in your data become as important as the data itself. When everything connects to everything else, in different ways, with different meanings. Think about what Facebook's data actually looks like. There are people. People are friends with other people. People live in cities. People attended universities. People worked at companies. People wrote posts. Posts contain tags. Tags reference other people. All of these are different types of connections between different types of entities, and you need to traverse all of them efficiently. That's not a table. That's not a document. That's a graph. A graph consists of two things: vertices, also called nodes or entities, and edges, also called relationships or arcs. Vertices represent things. Edges represent the connections between them. The book gives 3 illustrative examples. Social graphs: vertices are people, edges record who knows whom. The web graph: vertices are web pages, edges are hyperlinks, click a link and you traverse an edge. Road networks: vertices are junctions, edges are roads between them, and edges can carry properties like speed limit and distance. But here's what makes graphs especially powerful: they don't require homogeneous data. Facebook's social graph has vertices for people, locations, events, check-ins, and comments all stored in a single graph data store, with different types of edges connecting them. In a relational model, you'd need separate tables for each entity type and complex join logic to traverse relationships. In a graph, a relationship is just an edge. Traversal is the fundamental operation. The relational model excels when data fits in uniform rows with predictable joins. The document model excels when data is self-contained trees. Graph models excel when your data is a network of highly interconnected entities with varied relationship types. 2 graph data models have emerged as dominant, and they have very different design philosophies. The first major graph data model is called the property graph model, and it's the model used by Neo4j, the most widely deployed graph database in the world. In the property graph model, every vertex has 4 things: a unique ID, a set of outgoing edges, a set of incoming edges, and a collection of properties stored as key-value pairs. Every edge also has 4 things: a unique ID, the tail vertex it starts from, the head vertex it points to, a label that describes the type of relationship, and a collection of properties. Here's a useful way to think about it: a property graph is essentially 2 relational tables. One for vertices, one for edges. The edges table has a foreign key to the tail vertex and a foreign key to the head vertex. The book explicitly notes this equivalence: you can represent any property graph in a relational database. But the power of the graph model isn't the storage format. It's the flexibility. Any vertex can connect to any other vertex. There's no schema that restricts what types of relationships can exist between what types of entities. If you want to add a new relationship type, say, collaborated with, in addition to as friends with, you add it. No schema migration. No alter table. To query property graphs, Neo4j developed a declarative query language called Cypher. Cypher uses an arrow notation that makes the structure of a query visually match the structure of the graph. To express find all people who emigrated from the United States to Europe, you write a pattern using arrows: a person vertex, a born_in edge pointing to a location within the USA, a lives_in edge pointing to a location within Europe. Cypher's query optimizer handles the traversal strategy. The contrast with SQL is dramatic, and the next slide makes it concrete with real numbers. Here's a number that makes the case better than any abstract argument: the same query that takes 4 lines in Cypher takes 29 lines in SQL. That query, find all people who emigrated from the United States to Europe, with their names and birth cities, is a variable length traversal. You start at a person. You follow born_in edges until you reach a location in the USA. You follow lives_in edges until you reach a location in Europe. The number of hops isn't fixed in advance. Different people have different location hierarchies. Relational SQL wasn't designed for variable length traversals. SQL in 1999 introduced a feature called recursive common table expressions, though with recursive syntax specifically to handle this. You can write it. It works. But as the book says, it is very clunky. 29 lines of SQL versus 4 lines of Cypher. Both correct. One readable. One not. Now enter the second major graph data model, the triple store. Triple stores store all information as 3-part statements: subject, predicate, object. For example, Lucy, married to, Alan. Lucy, born in, Idaho. Idaho, within, USA. The subject is always a vertex. The predicate is either an edge label representing a relationship between two vertices or a property key representing a value attached to a subject vertex. This is the data model underlying RDF, the Resource Description Framework, originally designed to enable machine-readable data sharing across the web. The query language for triple stores is called SPARQL. And in the book's example, Sparkle is even more concise than Cypher for the same traversal query. The exact syntax looks different. Sparkle uses as a variable prefix and writes relationships differently, but the expressiveness is comparable. The existence of two distinct graph data models, two distinct query languages, and a dramatically verbose SQL equivalent for the same query tells you something important. The way you model data shapes the language you can write to query it. Graph models make graph queries natural. And for a third model older than either, that goes even further. Datalog is much older than Cypher or SPARQL. It was studied extensively in the academic database community in the 1980s, before either of those languages existed. Yet it provides the conceptual foundation that both of them build upon. The data model is similar to triple stores. You express facts as predicates with two arguments. Name, Namerica, North America. Type, Namerica, continent. Within, USA, Namerica. Within, Idaho, USA. Each fact is a statement about a relationship between two things. But here's what makes Datalog different from every other query language we've discussed. Instead of writing a query against the data, you define rules. Rules are new predicates derived from existing data. For example, you could define a rule called within _ recursive, a location X is within region Z if X is directly within Y and Y is within Z. Once you define that rule, you can query using it without knowing in advance how many hops the traversal requires. The rule handles any depth automatically. Rules in Datalog can call other rules. Rules can call themselves recursively. This lets you build up complex queries as a composition of small, reusable pieces. Datalog is used in production today. Datomic, a database created by Rich Hickey, the designer of Clojure, uses Datalog as its query language. Cascalog is a Datalog implementation for querying Hadoop datasets. It requires a different way of thinking. Most developers are trained to write procedural code or declarative queries. Writing rules that generate derived facts is a third mode closer to logic programming. The book is honest about this. Datalog is harder to get started with. But for complex, interconnected data where rules need to compose and reuse, Datalog's power is real. And understanding it completes the picture, from flat relational tables, to nested document trees, to interconnected graphs, to derived rule systems. These are not just different storage formats. They are different ways of thinking about what data means and how to ask questions of it. Choosing the right model for your problem is one of the most consequential architectural decisions you'll make.